All right, ladies and gentlemen, the lecture you're currently watching right now is a continuation of the ideas which we began in the first part of the modern atomic theory discussion. The lecture today is going to focus on what we refer to as an electron configuration, which is a representation of the electron positions within an atom as described by the Schrodinger wave function equation. So, let's go ahead and get started. The key idea we're looking at today is based around an idea that we are going to be filling electrons into orbitals within an atom. Recall those orbitals refer to the various different standing waves that electrons occupy as positions around an atom. And in filling these orbitals, we're going to be following what we refer to as the Aufbau process. The Aufbau process is a German term which means fundamentally from the ground up. And the idea here is that just like if you took a bunch of bricks and let them all fall into a pile on the ground, the very first bricks that are going to fall are going to occupy the positions of lowest potential energy. That is to say, they're going to occupy the positions lowest to their ground state. And electrons can act the exact same way as those bricks do. When we are filling orbitals in an atom with electrons, the electrons are always going to fill the lowest energy level orbitals first, following a sequence which is described on the handout which you've received in class of the Aufbau process. So if you can make sure, please, as you're going through the remainder of this lecture, that you have out that handout as well as your periodic tables. We'll use both those materials to kind of come to an understanding about how this electron filling process works for writing electron configurations. Now, in addition to that idea of the Aufbau process of filling the electrons from the lowest potential energy state on up, the second rule we're going to follow as we complete these electron configurations is what we refer to as Hund's rule. Another way of looking at Hund's rule is what we refer to as the bus rule. And what the idea here is, really, if you've ever sat down on a city bus and you walk in the bus and take a look around all the available seats, if there's only you and one other person on the bus, it would be a very strange and uncomfortable thing to do if you didn't know this person, to walk up and sit directly next to that person with all the other empty seats available. And electrons kind of do the exact same thing. If they are not forced to pair up with another electron within an orbital, they'll take an empty orbital first as long as it's at the same potential energy level. So that is to say, electrons occupy all the empty sublevels within a given orbital before they're forced to pair up. So what we're going to do here is I'm going to scroll down just a little bit here and have a look at this diagram. This diagram is a diagram of relative potential energy levels of the orbitals within an atom. And as you look at the very bottom of this diagram, you'll see way down at the bottom there, we have the lowest potential energy orbital, which we refer to as the 1s orbital. The 1 refers to the relative distance on average from the nucleus, 1 being closest to the nucleus. And the s orbital, as we discussed in the previous part of this lecture, the s orbital is referring to the shape of that orbital, which is, for an s orbital, a spherical orbital. So the lowest potential energy position an electron can occupy within an atom is in the first energy shell, closest to the nucleus, in a spherically shaped orbital. Moving on up, the second lowest potential energy position these electrons can occupy is now also a spherically shaped orbital, but now it's further from the nucleus on average, so it gets the designation 2s. And you'll see, moving up from there, in increasing potential energy, we move to the 2p orbital. The 2p orbital, if you recall, p orbitals are those dumbbell-shaped orbitals, and as we discussed earlier, those dumbbell-shaped orbitals can be oriented along 3 different axes, the x, y, and z axes, which implies, therefore, we have 3 different sublevels within that 2p orbital. So we move from 2p on up to 3s, followed by 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, and then continuing along up, 6p, and then 7s, followed by 5f. Now, this diagram, again, here shows the relative potential energies in kind of a visual way, a graphical way. The sheets which you have available to you designate the same sequence of relative potential energies of these orbitals but it's kind of diagrammed out with a series of arrows to follow from lowest potential energy to highest. So if you start in the upper position on your handouts there, your Aufbau handouts, you can simply follow the arrows, starting with the 1s orbital on the top of that Aufbau process sheet, that gives you levels of ever-increasing potential energy. So again, you go from 1s to 2s, and then over to the right to 2p, followed by 3s, 3p, 4s, and then once you reach that 4s orbital, you kind of have to go back up to the 3d orbital, and now you follow this sequence of diagonals throughout the rest of that process. So 3d, followed by 4p, and then 5s, and then kind of zigzag back around up to 4d, 5p, 6s, and then another zigzag back around to 4f, 5d, 6p, and 7s, and then final zigzag up here, 5f, 6d, and 7p. Now that Aufbau process sheet is a tool which you will have available to you on your tests, so I'd encourage you as you go through and do these electron configurations to use that diagram as a tool for determining the positions the electrons occupy within orbitals in these atoms. So let's take a look at a couple examples here. If we were to begin by looking at the simplest atom on the periodic table, a hydrogen atom. Looking on your periodic table, you'll notice that hydrogen is atomic number 1, which implies a neutral hydrogen atom has 1 proton and 1 electron. And what we want to do is we want to figure what position that electron is going to occupy in our electron configuration. Because of the Aufbau process, which implies the electrons will always occupy the lowest potential energy levels first, a hydrogen atom in its ground state is going to put that electron in the 1s orbital. And we're going to diagram that with a little up arrow in that 1s orbital, showing that that is the lowest potential energy position this electron can occupy. And when we write the electron configuration describing that process, the terminology we're going to use here is going to just tell us essentially what orbital we have electrons in and then how many electrons are in it, following the convention where we put the 1s, the orbital first, and then to show how many electrons are in that 1s orbital, as a little superscript, we're going to designate a little 1 up top. And this reads 1s1, which tells me for a hydrogen atom, there is 1 electron within the first energy shell in its strictly shaped orbital. Now helium, in contrast, helium has 2 electrons. Those 2 electrons for helium are going to, again, occupy their lowest potential energy positions. The lowest potential energy position electron is, again, going to be in that 1s orbital. The second electron that helium has, as an atom with 2 electrons, is also going to occupy the 1s orbital. We're going to designate this one with a little down arrow here. We call this electron spin down. And this is essentially going back to that idea, as we mentioned on the previous lecture, that each orbital, so each sublevel of an orbital can hold a total of 2 electrons spinning in opposite directions. We call it 1 spin up and 1 spin down. So for helium's lowest potential energy configuration, we're going to go ahead and give it the designation 1s, and then 2 to designate, again, that we've got 2 electrons within that 1s orbital. Now let's take a look at a slightly more complicated atom here. If you take a look at, let's say, nitrogen, element number 7, nitrogen with 7 electrons, again, is going to occupy those electrons in the lowest potential energy states according to our Aufbau rules. So if I go through and fill the electrons for nitrogen, starting in the lowest potential energy orbital, I would put 2 electrons in the 1s orbital, spinning in opposite directions, spin up, spin down. Followed by, the next lowest potential energy level is the 2s orbital, again, still spherical in shape, but further from the nucleus. 1 spin up, 1 spin down. And we've used up 4 of our 7 electrons, which implies the next 3 electrons need to go into the next highest level energy level orbital, that being the 2p orbital, those dumbbell-shaped orbitals. And the trick we want to follow here is this. I'm going to put 1 electron in the first 2p orbital on the 2p x-axis there. And the trick here becomes, again, where we need to apply our second rule, that is Hund's rule, or the bus rule. Rather than pairing off the electron in that same suborbital, in the 2px orbital, instead what we're going to do is put the next 2 electrons for a final 2 within the nitrogen's configuration into the other 2 orbitals at the same sublevel. Placing them here puts them at lower potential energy than if we were to pair them off, because remember, electrons are negatively charged, and negative charges repel other negative charges. So if we were going to pair them up in the same sublevel, that'll put them on average closer to each other, which would increase the repulsion and therefore put them at relatively higher potential energy. So following Hund's rule, we're going to fill the empty orbitals at a given level first before we start to pair them off. So our configuration for nitrogen, according to our diagram, now looks like 1s2 followed by the next highest energy level, 2s, in which there are 2 electrons. And then within our 2p orbital, we've got a total of 3 electrons. So we would read that configuration 1s2, 2s2, 2p3. And you can kind of see how we would follow this process for a larger atom. So let's go ahead and do one more example. Looking at a larger atom, we'll take a look at something like, let's say, chlorine. Chlorine is element number 17. So we need to occupy the 17 lowest potential energy positions for electrons within this atom. So looking at our chlorine atom with 17 electrons, let's just count them off, starting with the lowest energy first. It would be 1s2, 2s2, followed by, in the 2p orbital, 6 electrons in there. 1, 2, 3 spin up, according to Hund's rule, followed by 4, 5, and 6 spin down. We're now up to a total of 10 electrons, which we put into our atom. 11 and 12 are in the 3s orbital, followed by, in the 3p orbital, 13, 14, 15 spin up, followed by 16 and 17 spin down. So the electron configuration overall here for chlorine would be 1s2, 2s2, 2p6, followed by 3s2, and after that, 3p5. So I think with that, you should be able to see how filling energy levels within these orbitals on our diagram makes okay logical sense. We'll go ahead and take a look at a couple of more things here before we move on. We also are interested in chemistry at looking specifically at one particular position of those electrons, which is the electrons in the outermost highest principal energy shell, which we refer to as the valence electrons. You may remember from your biology days that those valence electrons are the most important electrons within an atom because those are electrons furthest from the nucleus at the highest potential energy level and therefore most accessible and available to be formed into chemical bonds. So one of the things we want to be able to get out of this idea and understanding is that there's a correlation that exists between the electron configuration for an atom and its behavior in terms of forming chemical bonds. So we're going to look at how we can determine the number of valence electrons within a given electron configuration for an atom. So let's go back and look at the example we just did there, which was chlorine. From our previous problem we just worked there, we found that chlorine's electron configuration was 1s2, 2s2, 2p6, 3s2, 3p5. Again, we just derived that on the previous slide. And what we're going to look at now is the electrons which are going to be available for bonding within this chlorine atom, that is the electrons in the outermost shell, the highest principal energy level. The highest principal energy level which we see filled for chlorine is the third energy shell. And there are electrons in that third energy shell occupying both spherically shaped orbitals and dumbbell-shaped orbitals. And that tells us that, in fact, there's a total number of valence electrons here of 7 for a chlorine atom, 2 in the s orbital and 5 in the p orbital in the third energy shell. So we say that this has 7 electrons in the valence shell. Let's do one more as a quick example here. Let's have a look at cobalt. Cobalt is element number 27, which implies we have 27 electrons which we need to fill according to our Aufbau process. And rather than using the visual diagram on the previous page, I'd like you to this time have a look at your Aufbau process diagrams on your handout sheets there, and we'll kind of fill through here. Something that might be useful for you on your handout sheet there is to just go ahead and label the number of total electrons which can be occupied by each of the different shapes of orbitals from our earlier in the lecture here. Recall those s orbitals can hold 2 electrons, so Next to the s's in there, you might just put a little 2 to notate how many total electrons we can put in there. P's can hold 6, D's can hold 10, and f orbitals can hold 14 total electrons there. So for cobalt, again with its 27 electrons total to distribute, that's going to give us an electron configuration starting at the 1s orbital, in which we can put 2 electrons. And then again, following the alpha process on your sheet, we would have 2s orbital with 2 electrons, the 2p orbital with 6 electrons. This brings us up to 10, followed by the 3s orbital with 2 electrons, and the 3p orbital with 6 electrons. We are now up to 18, followed by the 4s orbital, which can hold 2 electrons. And here's where you have to be careful. Looking at your alpha process diagram, recognize you now need to kind of zigzag back up now to follow those diagonal arrows to the 3d orbital. And we're looking like we're right now at 20 electrons we put into our electron configuration. So that d orbital, which can hold up to 10, will be able to hold all 7 of those remaining 3d electrons. So for cobalt, our configuration ends up as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. And here's where I want you to be very, very careful in terms of determining the number of valence electrons for this atom. It can be very tempting to look at this and say, hey, well, those 3d electrons are the last electrons I put into this orbital here. We call that the last filled orbital. However, if we recognize here that the 3d orbital, yes, is the highest potential energy orbital, that doesn't necessarily mean that those 3d electrons are the ones which are furthest on average from the nucleus, because the potential energy of the electrons is based not only on distance from the nucleus, but also on relative position with respect to the rest of the electrons within the electron cloud. And because we're packing those electrons in that d orbital in close to other electrons, there's so many in there in that third energy shell, they exist at higher potential energy, even though the 4s electrons are further on average from the nucleus. So the valence shell in this case is not the 3d orbital, that's the highest energy orbital. The valence shell, the place where they're on average furthest from the nucleus, is designated by the highest principal energy level. That is the 4th energy level, where we have 2 electrons occupying that spherically shaped orbital. So for cobalt, the valence shell electrons are in the 4s orbital, which means we've got a total of 2 electrons in the valence shell for cobalt. And let's go ahead and, just for giggles here, do one more quick example to check something that tends to cause problems on the test. Let's have a look at the electron configuration for element number 32, which is germanium. And again, in order to determine the number of valence electrons, we need to get an electron configuration. So following your alpha process sheet, again, starting at the top in the 1s orbital, we would fill 1s2, 2s2, 2p6. Following along will bring us to 3s2, 3p6, followed by 4s2. And after the 4s orbital, remember we zigzag back up, now up to the 3d orbital, in which there are 10 electrons occupied right there. And with that 3d10 configuration, that's brought us now up to a total of 30 electrons we put into our configuration. Meaning to get to germanium's number 32, all we need to do is in the next energy shell, which is the 4p orbital, we're going to go ahead and put those last 2 electrons in. So for germanium, we have the configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. And now to determine the number of electrons in our valence shell, all we need to do is, again, recognize that the valence shell is the ones at the highest principal energy level, that is furthest on average from the nucleus, which for this configuration appears to be the 4th energy level, the 4th shell. And within that 4th shell, we find that we have 2 electrons in dumbbell-shaped orbitals, the p orbitals, and 2 electrons in spherically shaped orbitals, which gives us now a total of 4 electrons in the valence shell. So again, the big key idea I want you to keep separate in your mind here is that the number of valence electrons is different from the number of electrons in the last filled orbital. The last filled orbital is that 4p orbital, in which there are 2 electrons. But the valence shell includes all shaped orbitals at that highest principal energy level. So that is all electrons occupying orbitals within the 4th energy shell. So both the s and the p orbitals in this instance. All right, so with that information, you should be good to go with enough information in order to complete your homework assignments on electron configurations. Thanks for listening.